Welcome back once again. Today there is another concept we are going to discuss, that is a characteristic of a ring. In the last lecture yesterday we talked about integral domains and fields and how they are related. And also we have seen that when an integral domain becomes field and when whether every field is a integral domain or not. The latter question was very affirmative, but in case of a integral domain to be a field, we concluded that every finite integral domain is a field. And then we saw some examples like ZP, where we proved that it is a field. Now there is another concept in this chapter. I think this is a concluding subtopic of this chapter. That is characteristic of a ring. So characteristic of a ring is moreover is just like we define order of an element when we discussed group theory. When we used to talk about suppose Z2 under addition. So in Z2 there are elements 0 and 1, and if we add 1 2 times, then we are getting 2 and this is 0. Okay. So what we can say here, 2 times of 1 equals to 0. So there exists a non-zero number here. This is positive, of course. So we are able to get some n, and like this equals to 0. Okay. The similar concept is translated into a ring. And because ring in general is not a group under multiplication, it is a group, abelian group under addition. So we can talk about this kind of thing only as of now. Okay. Okay. So, for example, if you take in Z3, like this Z3I, and this is a set of numbers of the form A plus IB, where A and B belongs to Z3. Okay. And in this set, how many elements? 9. Yesterday we have seen.
Yes, sir.
So,
3 square.
yeah. So if you take, if you see 3x, we can write it as x plus x plus x, and 3 times of x is this is. So this is going to be 0 because we are going to reduce every number here with multiplication modulo 3. Okay. So this is when this 3 is divided by 0. So it comes out to be. I'm sorry, this one is addition modulo 3. Na? So 3 becomes 0 here. Okay, 3 becomes 0. Okay, so what we got 3x equals to 0. So this is a non-zero number. Okay. Finally, if you see the subring of Z12, in Z12, subring of Z12 is the set. In Z12, let's consider the elements 0, 3, 6, and 9 is a subring of Z12. Okay. We can have 4 times of x. This is equals to x plus x plus x and plus x, and this equals to 0. Okay. This equals to 0. And this is true for all x. Okay. So based on this, we have the following definition of characteristic of a ring. The characteristic of a ring R is the least positive integer n such that nx equals to 0 for all x belongs to R. If no such integer exists, we say that R has characteristic 0. The characteristic of R is denoted by this. Okay. So because we are searching for least positive integer n, which satisfies this property, and this should be true for all x. So certainly this n is going to be unique. Though it seems like we are talking about the order, but here it is not order, but we are computing just like that only. Okay. We are searching for least n, natural number n such that nx becomes 0 and 0 for all x in that particular ring. So in one sense, we are computing like that, but it is unique for a ring. Okay, and this is when we talk about order of an element in a group, it is element-based property. So we search for small n such that n equals to 0. So in particular case of A, okay, we don't say for all A. So for each A we get different n. Okay, that maybe in some cases for different A n may be the same. But thing is that here we are not saying like that. But and also this characteristic is a set-based property. This is unique for a ring. You can't say that there are so many characteristics of this. Okay. Okay. So okay. Of course, if you see the example, the ring of integer. The ring of integers z. So characteristic, it's has characteristic. Characteristic we used to write like this. Okay, characteristics 0. Okay, that is characteristic of z equals to 0. You know, if you are searching for any n such that nx equals to 0 for all x equals to, for all x belongs to the set of integers. So what could be the possibility for n except 0? There is no such non-zero, there is no such positive n exists such that the source. So it means that if no such exists, then R has characteristic 0. Okay. So ultimately, we have concluded that characteristic of Z is 0. What about if you take Zn, characteristic of Zn? We need to search some m such that x equals to 0 for all, and this 0 is from Zn. This 0 should be in Zn. 0 should be in Zn. And this should be true for all all x belongs to Zn. So what could be the possibility? What are the possibilities for m? Can you tell me? Of course, m is non-zero number.
सर n हो सकता है, m is equal to n, 0 के अलावा.
Yes, so m equals to n. You can note down 1 point for this. M equals to 1. Sorry, n. That is this mx has to be multiple of. Sorry, this should be multiple of n. So in case you may be getting so many so many examples for here, from here. So in case of Z2, the characteristic is 2. In case
2.
of Z3, the characteristic is 3, like this. Okay. Okay, next, but thing is that it is sometimes difficult, or not sometimes, but if the ring as having so many elements, there are not two, three. If there are two, three elements, then of course one can easily verify. But in case the given ring has many elements, then it is difficult. So what are the possibility, uh, and what are the possibility for determining the characteristic of a ring? Whether there is any formula or any concept with the help of which we can determine without actually computing the characteristic. So there is a result which is recorded as a theorem in your textbook, and the theorem states that characteristic, that theorem talks about the characteristic of a ring with unity. Characteristic or a characteristic of a ring with unity. Actually, um, you know that a ring may or may not have unity. So here we are considering the characteristic of a ring with unity. That is ring with unity. Okay, that is multiplicative identity. Okay. So if there is identity, then things become simple. If you want to know what is the characteristic of a given particular ring, and this states that let R be a ring, let R be a ring with unity, and let us denote it by 1. If 1 has infinite order, if 1 has infinite order under addition, then the characteristic of R is 0. Then the characteristic of R is 0. And in other case, if 1 has order n under addition, then the characteristic of R is n. This thing we can see here. Let us see some example before going towards proof. If you see this example, or example number one, this ring of integer z, whether it has unity or not. Hello. The ring
Yes,
of
sir.
integers.
1 and
Yeah, it
1
has
and minus
unity.
1.
Identity is unique, gentlemen. I'm not talking about units. Don't get confused with units and unity. Unity is identity, multiplicative identity. Huh?
Yes, sir. 1.
Okay, 1. So according to this theorem, if 1 has infinite order, so you know that here 1 has infinite order. 1 has infinite order. Okay. So it's what is called, its characteristic is going to be 0. Okay. In other case, the example number 2, in case of Zn, if you add 1 n times, and this is the minimum number of times we need to add 1 to get n. This is 0 in Zn. All right. This is the minimum number. So therefore, order of 1 is n. That's what I was talking about. Actually, we are computing order, but the thing is that we are relating this property somehow with the ring, not with the element. Okay. So here, in case of Zn, or 1 has, that is a multiplicative identity, has order n, and therefore its characteristic is going to be n. So this theorem says that if you have a ring where unity is there, then the characteristic of that ring can be either 0 or n. That's all. That's all. Okay. And n is nothing but the order of n. Let us see the proof. If one has infinite order, then by definition, of characteristic of R, there is no positive integer n such that n times 1 equals to 0. Okay. No positive integer n such that n times 1 equals to 0. So this implies that characteristic of R is equals to 0. So because we cannot find any n, okay, that is order of n1 is not finite in one sense, you can say. If the order of 1 becomes infinite, then we say that characteristic of R is 0. That's all. Okay. And when I'm talking about the order of 1, it means what? It means that I'm considering all plus as a group, okay, not as a ring. Fine. Because we used to talk about the order of an element in a group only. Okay, suppose in case, suppose that order of 1 is n. Okay, I think you remember this notation. Order of 1 is n. Then n times 1 equals to 0. And since n is least positive integer, is the least positive integer with this property, so n times of x, we can write n times of x can be written as 1 into x, and this is equals to n times x by associative property. In a ring, we know that this property, because in multiplication it is closed and associative, that is semi-group. Okay, if you remember. So times x, and n times 1 is 0, and therefore 0 times x, and 0 times x is equals to 0 using the properties of a ring. Okay, so this means what? Nx equals to 0, and this is true for any arbitrary or for all for all x belongs to the ring. And because n is least, this implies that characteristic of R is going to be n. Okay. So this made the thing simple. Uh, what we need to know? We need to search if there is a multiplicative identity in that group, in that ring. If it is there, then our only task is to determine the order of that identity element. Okay. If order of identity element is infinite, then we say that the characteristic is 0. And in other case, if the order of identity element is finite, then we say that the order of characteristic of that ring is equals to the order of identity. Okay. And now uh, from this theorem, we know that a ring with the identity has only two possibilities. Either it has 0 or it has the characteristic n. And of course, here we don't know what is n exactly. But in case, if you talk about the integral domain, which are more particular case or a special case of ring, in which we don't have any zero divisor, okay, in which we don't have any zero divisor. So in that case, things become more simple and we get more crisp information about the characteristic. And what is that property in case of integral domain? In case of integral domain, we know we come to know that the characteristic of integral domain is either 0 or prime. That this n, uh, this n here was here in this theorem, n was the order of identity. But in case of integral domain, the order of 1 is going to be the prime number, and therefore the characteristic of that ring is going to be prime. So either 0 or prime. This is A. Okay. CHA. Okay. So next theorem talks about the characteristic of an integral domain. 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 Okay. So it says that the characteristic of an integral domain is 0 or prime. The characteristic of an integral domain is 0 or 0 or prime. This is not O, but this is 0. Zero or prime. So here we have more precise information. Let us see the proof. Proof is that in view of the last theorem, okay, we know that integral domain has identity or not. Hello, do you remember?
Yes, sir.
Yeah, it has identity, and it is also commutative because we have chosen the definition. We chose the definition where the ring was commutative with identity. Okay. So a ring which is which is commutative and having identity is called integral domain if it has no zero divisor, okay, or cancellation law holds. Okay. Yesterday we talked about that we can replace the having no zero divisor kind of thing with a cancellation law. Okay. So let us see. In view of Okay, let us write independent proof kind of thing. Okay. I don't know which where colors gone. Let us. Okay, this is something else or what? Okay. Sorry. Okay. Let us see. Since an integral domain has identity element and uh, so uh, so in view of the above theorem, uh, we need to show that uh, order of identity, यहाँ पे identity of 1 लिख दे रहा हूँ मैं, ठीक है ना? Order of 1 is prime. Okay, fine. That is additive order of 1 is finite and it must be prime. That is additive order of 1 is finite and prime. We need to prove this is our claim. Okay, because the above theorem says that it is either 0 or n, and that n has to be prime in case of integral domain. That's all we need to prove. Okay, so suppose that order of 1 is n. Okay, and let us suppose that n is not prime but it is composite. Okay, let us see n equals to s times t, where we are here we are leaving the possibility for s and t to be 1 also. Okay, we are not strictly saying that this is a composite, but let us assume that n can be written as in this form. Okay, so if we can prove that this neither s is 1 neither nor 2 is 2 is 1, then it will become what? It will become a composite number. Okay, अगर दोनों s और t दो में से कोई 1 नहीं होता तो कंपोजिट हो जाएगा ये, ठीक है ना? तो फिर हमें कंट्राडिक्शन कुछ ऐसा मिलेगा. But thing is that we are assuming that let n can be written as s times t, where s and t are greater than or equals to 1 and less than or equals to n. Okay, so we will try to find out the possibilities for s and t. Okay, then 0 equals to n times 1 because n is the order of 1. So we can write it like this. And also because we have assumed it, n equals to st. So let us write s times t and times 1 here. Okay. So this we can write s times 1 and t times 1. Okay. So what we have, 0 equals to s times 1 and t times 1. So the product of these two element is 0. And because S is an integral domain, so we must have S times of 1 equals to 0 or T times of 1 equals to 0. Why? Because R is an integral domain. R is an integral domain. Okay, so integral domain has no zero divisor. If the product of two elements becomes zero, then one must be zero. Thing is, okay. This is the meaning of having no zero divisor. So also since n is least, n is the least positive integer such that n times 1 equals to 0. So we must have we know that this is least number. Okay, this is the least number, and s and t are either they are equals to 1 or equals to n or in between them. Okay, so there are possibilities. एस भी 1 हो सकता है, टी भी 1 हो सकता है, या फिर दोनों में से कोई से जो है 1 भी हो सकते हैं. ठीक है. Of course, both cannot be n, otherwise it becomes n square in the right hand side. But the product of these two is n, not n square. So what we have, what we conclude from here, either s becomes n, अगर s n बन जाएगा यहाँ पे, तो t को क्या होना पड़ेगा? If s becomes n, then t has to be 1. Okay, so we have s equals to n or t equals to n. Okay, and in both the cases, if s becomes n, then t has to be 1. Okay, then t has to be 1. And if t becomes n, then this implies that s has to be 1. All right. Okay, it means that
Yes, sir.
दोनों में से एक को 1 होना ही पड़ेगा, है ना, in both the cases. In both the cases, so in both the situation or cases, either s is 1 or t is 1. Okay, it means n has no proper factor. N has no proper factor. समझते हो आप? If I'm writing 5 equals to 1, 5 times 1 or 1 time 1 into 5, तो इसके प्रॉपर फैक्टर नहीं हुए, क्योंकि एक ट्रिवियल फैक्टर आ ही रहा है. 1 तो रहता ही हमेशा. 6 लिखता हूं तो इसके ये प्रॉपर फैक्टर हो गए. समझ रहे हो? ठीक है ना. तो इन केस ऑफ प्राइम यहाँ पे कोई प्रॉपर फैक्टर नहीं होता है. ठीक है. So has no proper factor, and so n should be prime. Should be a prime number. Okay. So this was about characteristic of a ring and how we can find the characteristic of a ring. Okay. You might have come across many times in earlier classes. Suppose, for example, if you want to talk about the solution of this, x square 4x plus 3 equals to 0. So if you are talking about the solution of this, what we used to do? We used to factor this x minus 3 and x minus 1 equals to 0. And from here, what we used to do? We are in z set of integers. Okay. So we used to say that x is 3 or x is 1. Okay, both satisfying. And that is both value satisfying this equation. Okay. So why we were doing like this? Because z was an integral domain. Okay, the product is 0, but none of them is I mean, none of them is non-zero. Okay. Okay. So some of them should be zero. I need to say some of them should be zero. So either this is zero or this is zero, or we can write x minus 3 is zero, or x minus 1 is zero, like this. So this is the situation we used to uh, we used to we used to follow. Uh, we used to use when we were factorizing this quadratic equation, or cubic or biquadratic quadratic equation, or solving any equation. So this was a thing we were doing, but unknowingly, and this is possible in case of integral domain. And you also know that, of course, in a group, the cancellation law hold. But with some least property, we can also that cancellation law hold here. Okay, that a property we see that we can say that if it has no zero divisor, so which is equivalent to the cancellation law in case of integral domain. Okay, so with this, this was the last topic. Okay, we concluded every topic from the chapter number 13. Yeah, of course, questions are there. So I think we should start taking from tomorrow those questions. Huh? So I will try to
Yes, sir.
take up the questions from exercise problem tomorrow. Maybe we can take tomorrow and day after tomorrow also, chapter 12 and chapter 13. So I will be very brief and short, and very selective questions I will be discussing. Okay. And if you want some particular questions to be answered here, so you can send me message in advance. Okay. Maybe tomorrow we can discuss chapter 12 or 13. I think let us discuss chapter 12 tomorrow, and day after tomorrow we can take up a chapter. I don't know. Tomorrow is Thursday, yeah? So we don't have any class on Friday. Yeah. So maybe on Monday we can take
Yes, sir.
exercise problem. Yeah, we can take the Monday. We can take on Monday. So by that time you can choose the questions. Okay.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.